Hey, good morning, everybody. I hope you guys are doing well. Um, let's take a look here at some things that I said I was going to do for you guys. Let's go to the browser. And before I do that, let's go to our homepage. So, okay, browser here. Now, what you guys have, if we go to 262, okay, going to 262, there we go. Online transition. A couple of things here. I have the lecture on alternating series. I also have those additional examples that I promised you guys. And some of those examples include the factorials that were requested. So double check there. We have some good, interesting examples for you guys. I did that yesterday afternoon. It was uploaded yesterday. And I connected it to Canvas this morning. So, and the website, by the way. So if you were a subscriber, definitely that will be there for you guys as soon as it's up. So you might have gotten that yesterday. So, ladies and gentlemen, this stuff has been there for you guys. So you have additional examples. And again, I put it in Canvas, and so you probably even get that notification there. So today what we're working on is an additional test known as the ratio test. And it deals with, there's really only two additional tests left, and it's based on the same idea that we work on today, ratio test and root test, but it's based on looking at convergence of what we call absolute convergence. Now, let me describe what that means. So let me actually describe what we're really talking about. You see, we've been working with series here that look like this essentially, where we say, okay, this is A1 plus A2 plus A3. So here's our series. What we're going to do here, and I just want to remark that every term here can be positive or negative. There's no restrictions here on what the signs of the terms are. This is a general series. So because this is general, there's no restrictions. What we're going to focus on today is we're going to take the absolute value of these, which means we're really having the sum of these terms. And what the effect is, if we take the absolute value of every term, we actually make these series, I should say, positive. Right? If they're already positive, there's no difference. If some of the terms are negative, well, turning them into positive, well, it makes the terms positive, okay? So the idea behind this, though, is to note that this relationship, that if I take, in general, any series and make some of those terms positive that may not have been, we have this relationship that the series is less than or equal to the sum here of the terms where some of them are now positive. So here they can be, some terms can be negative. All right. And what we just did over here by taking the absolute value is that we force the terms to be positive here. So now they're positive. And this is going to be a big deal. And I say it's a big deal because of the fact that I'm going to show and prove this to you guys later, that remember, here's the claim. I'm going to write this as a claim. And before I do that, I have to give you a definition here. Right? So let's start with a definition. And of course, we're going to care about whether this particular series here converges. So we want to know if that series converges. So we say here, a series converges absolutely. It's called absolute convergence. If these terms are finite. So if we add these terms forever and it adds to a finite value, then we say that this series converges absolutely. And this is known as, AKA, absolute convergence. Okay, so it's absolute convergence. And then you might say to me, why do we care about absolute convergence? Well, go back here to this relationship, and here's why you care. That if a series converges absolutely, meaning we took some of the terms and we made them positive, then that means the series actually converges by the comparison test. So here's the fact here. If a series converges absolutely, then the series converges. And this is, I'm gonna prove this here for you. Here's going to be the proof. Here's how we look at it. We can get the right color. So we start by assuming this particular series converges absolutely. Then what that means here is that by taking these terms to all be positive or at least greater than or equal to 0, right? This is the assumption that this is finite. That sum, that infinite sum, adds up to a finite value. And these are all positive numbers here. And then we're going to observe something here that's going to be the key. We want to observe this relationship that zero is less than or equal to an plus the absolute value of an. Okay, because what we're saying here is if you take a term and I essentially make it positive if it's negative, and I add that positive and the negative the same values, well, then you'll get 0. But if the term is positive and I add another positive value, well, of course, that's going to be bigger than 0. So far we know that this observation is correct. And then we can say that this is less than or equal to double the positive value. So the key to this proof is this inequality here. And this is true for all values of n. Okay, so that's pretty much saying if I take a term and whatever that term is, I can add that positive version of it, and that's still going to be less than or equal to double the positive version. And that's where this is, that's what's going to make this proof work. And you say, well, why is that? Because this implies, ladies and gentlemen, that if I now add the terms together, we want to know then what happens here to the sum of twice the absolute value of n. Well, that's equal to, if I pull out my constant by properties of series, that's twice that sum, which we know is finite. Okay? So you might say, okay, well, what happens now with all of this? Well, I'm sorry, hold on. I'm getting my seat squared away here. Okay. So we know that this is valid so far. And then you say, well, okay, that also implies, right, that the sum of an plus the absolute value of an, that has to also be finite by the comparison test. Because again, if you're looking back at these particular terms right up here, right, this version and this version, if we take the sum, we have the larger series converges implies that the smaller series converges. And that's by the comparison test. So we know, okay, this is also convergent. And then you want to also make another observation, right? Since this is finite here, that infinite sum is finite. So here's what I want to also observe. That is, it is certainly true that if I say to you, this series is equivalent to an plus the absolute value of an minus, I'm going to say, the absolute value of an. In other words, even if I didn't have these parentheses, and I'm not going to, let's leave it this way. What we're saying is that this term subtracted with that term, well, that's 0. And you're just left with the an term, is what we started with. So, okay. Now, by properties of series, you get sum an plus the absolute value of an minus sum absolute value of an. And yet again, we know that this here is a finite value. And this here is a finite value. Because the original assumption right up here is that we have absolute convergence. And this is what that means. This is finite. And we show that this is finite. And what that implies, ladies and gentlemen, that this series here is finite. So we just showed here then, since these are finite, this is all less than infinity, we can say here, i.e., in other words, that the original series here that we're talking about is also finite. And this is a very famous statement that absolute convergence implies convergence. Now, that kind of makes sense if we go way back up here, which we started the lecture with by saying to you, we're going to be concerned really with this idea. And let's kind of draw a rectangle if we can. Okay. And yeah, by comparison, if we have this absolute convergence, well, then we're guaranteed to have convergence. Okay, and that's really the issue. We care about convergence of a series, but sometimes we step out because remember, yesterday we covered alternating series, and some of the terms are negative. And if you look at some of the homework I did for you guys, some of those examples, you see some, the sign n pi over 2 had some terms with 0. So double check that video. It was very useful for me. It's very fun to go through the details and say, oh yeah, these are interesting things. And so those are some good details for you guys, getting you extra examples there. But, we have to step out because of the fact that some terms may be negative. So we're going to say, okay, if we can show convergence absolutely, if we make all the terms positive or at least greater than or equal to 0, and we have convergence there, if we make it a bigger series, remember, this one is bigger. If we make it a bigger series and it in fact converges, then that implies that the smaller series will converge or is finite. And that's the essence of this idea. So this is called absolute convergence. Let me give you guys a couple of other definitions of what we can encounter. Because remember, here's something you guys want to note. Here's something we can say, for example, -1 to the n over n. Here's a situation, or I should say, let's change this here. Let's put power 2 here. So let's kind of look at these situations here, and we're going to show an example of this. We're going to say, okay, here's our original series. But what we're going to consider is what happens to this series. Absolutely. And for this portion here, for today, your focus is going to be on the absolute value here. And so you're going to have to do a little bit of algebra and know by the quotient rule, here's what you get. And then understand that since we're dealing with natural numbers, our index here, right, n is 1 to infinity, right? This means that n squared will be positive, which means I can get rid of the absolute value. Okay? By definition of absolute value. And then in the numerator, I think we showed in the past, and I think what you guys really want to know is that you're going to see a lot of this. And what this means by definition is you have -1 times -1 times -1, and you have really n of these. We say n of these because of the power, right? Because of your exponent. And product rule for absolute value. And yes, again, you have n of these as well. And you guys know that this is really 1 times 1 times 1, n of these, which is 1. So you're going to see today and, you know, in your future, this portion, it's good for you to know that this is just 1. It'll save you some time. And so we really have this particular series, which is 1 over n squared. So when I take this absolute value, it is equivalent to the series of 1 over n squared. So we made every term positive. This is an alternating series originally given to us because it has an alternating mechanism, right? This is alternating. We made every term positive, and we noticed when we did that, you obtain the very famous, or you obtain a p-series. And in fact, this is a convergent p-series. So you have a convergent p-series, ladies and gentlemen, and what that means is that this particular series that they gave us to start with, it converges absolutely. And that implies that it actually is convergent, since absolute convergence implies convergence for the series. And this is the idea. This is finite, this sum. So this is what we're talking about, ladies and gentlemen. This is what we want to do, is we want to take a look at some of these alternating series, really, and show that they converge absolutely. And if they do, then we have general convergence. Now, that's a good example. It's typically an example that people use in the book. Here's another common example that people use in the book because it's important details. They're very fundamental. They're going to give you, and it doesn't matter how we write this, but they can say, you know, n or n plus 1. And this is the very famous alternating harmonic series. Now, this is not the harmonic series. It's the alternating harmonic series. Meaning we have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus, and that goes on forever. Let me double check to see. Yeah, n is 1. We get n plus 1 is 2, and that squares that -1. Okay. Yeah, you get the very famous alternating. In other words, these terms are alternating. And yesterday, what we looked at was the alternating series test. So we know a couple of things. I can say, just looking at the work from yesterday, that B and here is 1 over n, and this is a decreasing sequence, really. Okay, it's decreasing. We also know that the limit of 1 over n equals 0 as n gets big. So since it's decreasing and the limit is 0, here's what I know about this alternating series. This alternating series converges by the alternating series test. So we have knowledge. We could have answered this question, yesterday. And again, it's not the harmonic series, it's the alternating harmonic series. The signs alternate, meaning some of them are negative. And that subtracts, and that makes this infinite sum, if you recall, the harmonic series is actually a divergent series. That's a strict sum. But since we subtract some of those terms, it's now finite. And that kind of makes some sense. Now, if you said this question, is it absolutely convergent? The answer is going to be, well, let's see. We're now going to take that same series, and you say, what was the series? Well, it's alternating harmonic, 1 to infinity, negative 1 to the n plus 1 over n. And if we take these values, make them all positive, you guys know where we're going with this. What we can see now, the absolute value of n plus 1 over n, doing properties or using properties of absolute value again, like we did, we get 1 over n. So that this series in absolute value is equivalent to 1 over n. And you may say, well, we know this. This is the infamous harmonic series. It's not alternating, and that's divergent. This sum is infinite. So the question of, is it absolutely convergent? Well, the answer is no. So what you can have, ladies and gentlemen, is a situation where a series is not absolutely convergent, but the series does converge. The original series, the original question. We get convergence here because it's alternating harmonic, but absolutely it does not converge. And that's, remember, going back, essentially looking at that relationship, something like this, all they're saying is that this portion here is infinite in this example. And they're just saying that the larger series is divergent. Well, that doesn't mean anything necessarily with the smaller series. That doesn't imply, that doesn't guarantee. So the smaller series can be either finite or it could be infinite. We don't know. The comparison test, and I would say you can't even use the comparison test because it doesn't even apply to this situation. They're just saying that this portion here is infinite, and any finite value certainly is smaller than infinite. That's true, but it doesn't give us a conclusion about this series. So, I want to illustrate that point because we do have another definition for you guys, and that's called conditionally convergent. So we have a definition, and I want to get you guys these definitions here. A series is called conditionally convergent. If it converges but not absolutely. Okay, now let me tell you what this really means. They're saying that the series converges. This series is finite, but in absolute value, it's divergent. It's the prior example that we just did. The alternating series, alternating harmonic, is conditionally convergent. So it's conditionally convergent. Okay. Now, we're going to go to something that's another kind of example, I guess, if we do something like this. I mean, your book does. I guess let's just cut to the chase here. Let's do that. Let's cut to the chase. We have a very special test for absolute convergence. So these are tests for absolute convergence. And let me do it here. Here's what they're called. You have what's called the ratio test, and you have the root test. So you have two tests, the ratio test and the root test. These are tests for absolute convergence. Now, here's the ratio test. Let me see how the book writes it, and I can tell you how I write it. Oh, I guess I wrote it the same way the book does. Okay, no big deal. Okay, so here's the test. Number one. There's really three criteria. If the limit of the absolute value of the ratio of an plus 1 over an, this is really the ratio of the next term to the current term, equals Al. And this thing has to be smaller than 1. If you have this situation, then the series an is absolutely, I got to remember, I got to wake up. Got to wake up and remember how to spell absolutely here. It's harder than you think. You can't talk right at the same time and think. Absolutely convergent. And you might say, okay, it's absolutely convergent. Yeah, it just means that what we've been saying here, it means that this is finite, and really why you care is because that means your series is finite. You care about convergence of the series. So this is probably the thing you're going to be looking for with the ratio test. And like I said, they call it a ratio test because you're taking a ratio of a future term and a current term in absolute value. The second criteria is if the limit of that ratio of the future term and the current term, if that limit equals L and is bigger than 1, if that value is bigger than 1, then essentially we say the series diverges. And symbolically, that means sum an equals infinity. So if that limit of the ratio is actually larger than 1, we have divergence. Situation 3, if the limit of the ratio an plus 1 over an, if that limit equals 1, then it's inconclusive. Then the test is inconclusive. We don't know. It can converge or diverge. Okay, you have to take another approach. Anyway. So here's the ratio test, and let's call it that. And there's a root test version, but we're not going to talk about that one today. We're going to talk about the ratio test today. And I just want to make sure we could get started on the ratio test here, right? So let's actually see some examples of this ratio test. So we have the sum, -1 to the, this is the alternating mechanism. And then we have n cubed over 3 to the n. It's kind of a little dyslexia there, right? Some weird, you're taking an exponential and you're taking essentially a third power variable there. And we're switching the values here. Okay. Now, this here, ladies and gentlemen, is always an, because they're giving you, this is the an they're talking about. And so what you're going to need to start to do is make sure you write down that an is -1 to the n to the third power over 3 to the nth power. And what you're going to also do, and this is what we call, or I call the current term, right? This is current. The next term, you're going to have to get used to writing as well. Now, this is an plus 1, right? This is not an. It's the next term. So all you do is you replace, wherever there is an n, you replace it with a n plus 1. So this is now n plus 1 to the third power over 3. The power here now is n plus 1. So you have this ratio. Of this ratio yet, you have this n plus 1 representation. Okay? So you got the an representation, the current representation, and you have the future an plus 1. Because we need to write, ladies and gentlemen, and I guess I don't know what color to use. I get a little, I don't know if I want to go purple today. We need this ratio here. an plus 1 over an in absolute value. We need to see what that is, because we're going to take the limit of that. And if you guys want to see the proof of the ratio test, by the way, it's in your book. It's a nice read. It's a very clever thing. That's really what mathematics is, by the way. But, for sake of time, we're going to go to the ratio test, and you could read about the proof. And let me show you guys something here. Your real work is going to be in the algebra. So I'm going to say you start by putting that negative, the future term, let's just say, right? The an plus 1 term. And then you divide by the current term, which is -1 to the n cubed over 3 to the n. Now, you always get, or I should say, you usually get a complex fraction here. So it might be good to start, if we have some space here, do I dare? Oh. It might be good for you to start to write this way if you know you're going to get a complex fraction. Oh, I don't have space. Sure enough. If you know you're getting a complex fraction, -1 to the n plus 1. I'll show you what I'm talking about. N plus 1 cubed, 3 n plus 1. You're now going to multiply by the reciprocal. So you may want to go there, just to let you guys know. 3 to the n, -1 to the n cubed, because you have a complex fraction and you are dividing, remember? So we're having a division here of two fractions. Division of two fractions, and that is going to be multiplied by the reciprocal of that second fraction. Now, the rest here, if you guys want to know the truth, this is nice and fun. The rest is algebra. So you're going to be using some algebra skills here, ladies and gentlemen. This is what I mean. negative 1 to the n plus 1 power is negative 1 to the n times negative 1 times n plus 1 cubed times 3 to the n. That's over 3 to the n times 3 times negative 1 to the n times n cubed. Okay, so I just use properties of exponents here, right? And so now what's going to happen is we get to cancel, and you say, well, what are we canceling? Well, this portion goes away. And it looks like this portion goes away. And so all we're left with is this negative 1, n plus 1 cubed, this 3, n cubed. We're left with this. And here's what you end up getting here. It's the absolute value of negative 1 times the absolute value, n plus 1 cubed. All right, let me do every detail for the first example, right? People appreciate that. Negative 1 times n plus 1 cubed over 3 times n cubed. And this is in absolute value. All right. Now, I'm going to do a few things here. I'm going to take out, use properties. Absolute value of negative 1, absolute value of n plus 1 cubed, okay? Absolute value of 3, absolute value of n cubed. So I'm using properties of absolute value that when you divide, we can, separate those terms. And when you multiply, we can separate the terms. So really, we can separate every term with an absolute value. Some of these things, like this is going to be 1, and this is going to be 3. And this here is just simply n plus 1 cubed, and this is just n cubed, ladies and gentlemen, because of the fact that n is natural numbers, 1, 2, 3, 4. So anything, by definition of absolute value, you just remove the absolute value signs. If you guys recall that kind of definition, right? You say, what are you talking about? It's piecewise. You use this if what's under the absolute value is positive or 0. You use opposite of that if this is less than 0. Okay. So you end up now with this relationship. You end up with 1/3 n plus 1 cubed over n cubed, which is really 1/3 n plus 1 over n cube, if you want to look at it that way. And I mean, it might be, you're going to look at it that way. I'm just going to say this is the absolute value of the ratio of the future term and the current term, because we have to take the limit of that now. And we want to see this limit as n goes to infinity. We want to see if that limit value is smaller than 1. So when you take that limit, you're really looking at 1/3 n plus 1 cubed over n cubed as n gets big. Factor out your 1/3. You really have the limit of n plus 1 cubed over n cubed as n gets big. And you might say, I did this limit. This is why I wanted to put it back, because I want to go through the details. You might say, oh, Mr. Judge, that's indeterminate. And you're right, it is indeterminate. So when you have an indeterminate situation like this, you're going to have to consider, do you use L'Hopital's rule? Maybe. Or do you use algebra, right? I'm going to say in this case, use algebra. And what that means is you have this portion here when we're using that algebra. That's really n plus 1 over n cubed. Again, properties of exponents. And then this portion becomes n over n plus 1 over n cubed, which is really 1 plus 1 over n cubed. So we have 1/3 times that limit of 1 plus 1 over n cubed as n gets big. And what you guys know is that this will be 1/3 really times 1, which is 1/3. Because as n gets big here, if I try to find this, we're looking at that ratio here. As n gets big, right, 1 over n goes to 0. So you can write down the logic as n gets big, 1 over n goes to 0, which means 1 plus 1 over n goes to 1, which really means 1 plus 1 over n to the third power goes to 1 to the third power, which is equal to 1. And that's how we got the value for 1 here. And 1/3 times 1 is 1/3. And ladies and gentlemen, that very much is smaller than 1. So we showed here that the limit, where is that language? Oh, right here. We showed that this ratio is smaller. Well, it's equal to 1/3, first of all. And we know 1/3 is smaller than 1. This here is what you're going to be doing when you're working with the ratio test. And then ultimately you'll see the root test, but that's not today. So that value, that limit is 1/3. It's smaller than 1. And so you say, what does that mean? It means the original series. Go back over here. The original series. This is absolutely convergent. However, you really know that that implies that the original series is simply convergent, because absolute convergence implies convergence. I should say convergence without the absolute value. That's what that means. So this original series, we know this converges. So it's another test for convergence, but it's directly testing for absolute convergence, which implies convergence. So it wouldn't even be bad language if they just removed this phrase absolutely and just said the series converges, because it implies it. But you want to be exact. You want to show, guess what? It's absolutely convergence, and anytime that happens, we proved already that the series converges. And the real test is the original series. So anyway, that's your first example of the ratio test. And you really need to see and work with more examples. So I'm probably going to give you guys, extra examples as well for this. But anyway, let's see some more examples. Okay, and yesterday we had some requests for factorials. Well, guess what? If you are in the mood for factorials, let's see, is Marbella here? If you're in the mood for factorials, you came to the right place here. So let me show you an example with factorials. Right, here's a series that involves a factorial. And if you guys remember, the definition of a factorial, n factorial, by the way, is n times n minus 1 times n minus 2 all the way down to 2 times 1. Right? That's what we mean by factorial. So you start with the value n and you really count backwards until you end up with 2 times 1, and then that's multiplication. Remember, this is the an term. And we need the ratio. We need the next term, right? We need an plus 1. So since an is n to the n over n factorial, the next term, replace n with n plus 1. And that's how we get the an plus 1 term. And you say, okay, Mr. Judge, do we take the ratio and absolute value of those? Yes. But let's be smart about it, right? We start with the an plus the future term here, because this is my numerator, right? an plus 1. And we're going to be smart about this. I know we can write it as the quotient as it's given, but we're going to what again? We're going to multiply by the reciprocal. So this will save you a tremendous amount of time if you start to get used to that. If you know, for example, that dividing two, fractions will give you multiplying the second by the, by the reciprocal or the denominator fraction. It's a complex fraction. And you're always going to use algebra. And, that's the Achilles heel for some students. So definitions of exponentials, just these properties, right? N plus 1 power, that's n. Okay, this is n factorial. All right. And then we have n plus 1 factorial times n to the n. So I want to double check here because, like I said, it's a lot harder than you think to talk, write, think, all at the same time, and spell, by the way. So let me double check these things. This is why you could go, okay. All right. So do we have more Bella here with these factorials that she wants to see? Hopefully, right? Let's take a look here. What do we do with this? We're going to have to see what's going on here. So we look at this thing and you go, wait a minute, I don't see anything canceling. What's going to cancel? I don't see anything interesting canceling here at all. Well, the reason I mentioned factorial is because this portion here, here's what you're going to say. This is n plus 1 times n minus 1, n minus 2, all the way down to 2 times 1, if you focus on that. Now, I want to remind you guys or indicate that that is really the definition of n factorial. So by just looking at this n plus 1 factorial, I get the expression n plus 1 times n factorial. That's the key here. Because when we look at this here, we get n plus 1 to the n times n plus 1 times n factorial, everything over n plus 1 times n factorial, n to the n in absolute value. So n plus 1 goes away. Hold on. N plus 1 n factorial. Oh, yes, n plus 1 goes away. Sorry. Wasn't imagining that. And then n factorial goes away, right? So you're left with simply n plus 1 to the n over n to the n. And we know, since we're dealing with natural numbers, the absolute value goes away. You have n plus 1 to the n over n to the n. And by properties of exponents, you got n plus 1 over n to the n, which becomes 1 plus 1 over n to the n, algebraically speaking. So that means the limit now of an plus 1 over an is the limit of 1 plus 1 over n to the n as n gets big. Okay, now, if you took this course and you studied L'Hopital's rule, you say, oh, that's 1 to infinity. And that's an indeterminate power, right? So I'm going to say there's a procedure that you go through with an indeterminate power. However, I'm going to remark about this. This is a very famous limit. This is the limit, which is really the definition of E, the exponential number. So some of us, I teach various math courses. This is E, the exponential number. And, so I know this. However, if you said, oh, Mr. Judge, I don't know that, well, what do I do? Well, remember what you guys do. You let y be 1 plus 1 over n to the n. You take the natural log of y to both sides, if you guys remember that. And this gives you, by power rule, n, natural log 1 plus 1 over n. You guys remember this. You go through the process of evaluating that improper, I should say, the indeterminate power process. And you're going to find that this is actually going to be E. And you have to know the value of E because, remember, E here is approximately 2.718, and that's actually bigger than 1. So this value is larger than 1. And because it's larger than 1, ladies and gentlemen, that has great meaning for us. And we can say, well, what does that mean? Well, let's go back to the ratio test. It means that if it's bigger than 1, this is situation number 2. The series diverges. So what you can say now for this example is that this particular series diverges by the ratio test. So we have divergence by that ratio test. We should have said up here that we had convergence, right? And we can say converges by the ratio test. So this is the kind of work that you guys will start to see with some of these examples and problems. And the devil's in the details, meaning you're going to be using some algebra and really limits from Calculus 1 and at times maybe even Calculus 2 if you have to use L'Hopital's rule, if you have an indeterminate quotient or indeterminate power, indeterminate difference, who knows. But those are what you're really doing, if I should say, is you're using your various limit skills. And that's why that first exercise, or I should say examples on, I gave you sequence examples, looking at these limits is kind of important because it's the foundation of what we're doing. So, yeah, you're getting extra examples and they're very helpful. Let's try another example here. Negative 2 to the n over n squared. We're going to see how this works. And remember, this is your an, so we say an is negative 2 to the n over n squared, and the next term, an plus 1, is negative 2 to the n plus 1 over n plus 1 squared. Hey, Marbella, how you doing? How you doing? I hope all is well. We were doing some factorials. So, I put some up for you. Or I'm sorry, not for you, for everybody. For the alternating series examples. And then I also put some here today. So you're going to see factorials galore with the ratio test. All right. So you came to the right place. Anyway, here's an example that doesn't have factorial, and hopefully I'll get to some that do. But if I don't, I'm going to give you guys again more examples online. So that's my goal. Okay, give you more examples because people appreciate them. We need the ratio, and I got to stop talking and writing because if I do that, I'll make mistakes, right? Absolute value an plus 1 over absolute value of an. Remember, start with the an plus 1 term. Multiply again by the reciprocal because you really will get a complex fraction. And now use algebra. And you say, use algebra on what? Use algebra on your exponentials. And you go, okay. Again, at this point, properties of absolute value. The absolute value of a quotient is quotient of absolute value. Absolute value of a product is product of absolute values. So we just write down what everything is. Absolute value of negative 2. And remember, n's positive. So n squared is positive. So we get to, really remove the absolute value signs wherever there's a variable n here. So this is 2n squared over n plus 1 squared. So this is, again, the absolute value of the ratio. So we need to take the limit of that. Right? That limit's going to equal, guess we can put it over here, 2n squared, n plus 1 squared, and you get to factor out the 2, limit n squared, n plus 1 squared. And again, you get to use the definition of, or I should say, properties of exponents. It's kind of beginning algebra-ish. And here's where we're at, I guess. Okay. And then I'm going to say, you know, what is this? There's a couple of ways I can look at this here. Remember, this really, we can say is 2. I can put the limit here of n over n plus 1 to that second power. Or I could just simply look at, you know, what happens to this as a limit, which is the same sort of thing. You know, we're doing that directly. And we're going to use calculus 1, I guess, divide by every term or the variable with the highest power in the denominator. So like I said, your limit skills will come into play here. 1 over 1 plus 1 over n. And don't forget that answer is going to be squared. Well, you guys know this portion goes to 0, which is really 1 over 1 plus 0, but the limit then we say is 1. And so we get 2 times 1 squared, which is 2 times 1. And ladies and gentlemen, that limit is 2. So this limit here is 2, which is bigger than 1. Oops. This is what we want to look at. Limit's 2, bigger than 1. That means our series diverges by the ratio test. So we can say this diverges by the ratio test, which really means the sum is infinite, right? Your sum's infinite. So here's the language we look for. And here's the justification by ratio test. So here's a divergence situation. So let's look at some time here, and let's look at another example. Oh, let's see if we have time for this one. Hopefully we do. Here's a good one. Right? Remember I said we want to get some factorials in. 1 to infinity, negative 3 to the n, over 2n plus 1 factorial. Okay, this is our current term. This is an. So if we say an is negative 3 to the n over 2n plus 1 factorial, and the next term, an plus 1, is negative 3 to the n plus 1 over, be careful, this is n plus 1 plus 1. Remember, you get the next term, ladies and gentlemen. You get the very next term by simply replacing for this. You're looking here, and you replace this with n plus 1. So I was careful to say, okay, there's 2. There we go here. Replacing n with the n plus 1. Okay, so be a bit careful with that. And you say, well, what does that mean? Well, it means this is 2n plus 2 plus 1. It means you have 2n plus 3, really, factorial. So the next term is negative 3 n plus 1 over 2n plus 3 factorial. So let's see the ratio in absolute value. Start with that an term, because you're going to get a complex fraction, 2n plus 3 factorial, times, and remember, write the reciprocal. This is 2n plus 1 factorial over negative 3 to the n. And now here we get to use some properties, right? So we know we have a property of exponent there. Negative 3 to the n times negative 3. This is 2n plus 1 factorial. And I'm going to say focus at the moment here with this 2n plus 3 factorial. You see, 2n plus 3 factorial, I'm going to put this down here. This factorial is larger than this factorial. This is 2n plus 1 factorial. So the definition, remember what factorial is. You start with the term and you count backwards. So this will be 2n plus 2, and then 2n plus 1, and then 2n, and that goes down to 2 times 1. So you start with the term, and you count backwards, and you multiply, and you end here with 2 times 1. Now, I want to focus on this portion here, because I'm going to say to you or remind you that 2n plus 1 times 2n, and then there'll be a 2n minus 1. This is really 2n plus 1 factorial by definition. So I'm going to describe 2n plus 3 factorial as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. That's going to replace this right here. So you're going to say, oh, 2n plus 3 times 2n plus 1, I'm sorry, plus 2 times 2n plus 1 factorial, and then don't forget you had the negative 3 to the n down there. Now the reason you do this, you want to write it this way, is because your 2n plus 1 factorials are gone. You want to cancel. And then you know negative 3 to the n is also gone. So you're really left with these terms. You're left with negative 3, 2n plus 3, 2n plus 2. So we have this absolute value here, negative 3 over 2n plus 3 times 2n plus 2. And again, now properties of absolute value really means I have the absolute value of negative 3, and I'll put it this way. I'll just use the quotient rule. Okay, I can use both quotient and product down here. And again, absolute value of negative 3 is 3, and this is just a 2n plus 3 and a 2n plus 2 here. So you end up getting 3 over 2n plus 3 times 2n plus 2. So now the limit here of this absolute value ratio is what we're looking at. You're really taking a look at the limit of 3 over 2n plus 3 over 2n plus 2 as n gets big. And ladies and gentlemen, you know this goes to 0 now. This limit is 0. Let me get rid of the box. I mean, we could keep the box, but the more important thing is that in relation to 1, this is smaller than 1. So this limit here being 0 implies by the ratio test, the original series that we're talking about, this thing will converge. Well, let's go through the logic. This converges absolutely. We have absolute convergence, which implies convergence. So this sum is actually finite. And that arrow means let's put some space here. This is kind of, that arrow means, ladies and gentlemen, is an implication in logic. So here's what we say. We have absolute convergence implies convergence. This sum is finite. So yes, in this section, you're going to see factorials. You know, a lot of factorials. And what I will do for you guys as well, of course, as I've been doing, is I will give you guys more examples of the ratio test. And hopefully we could get that done today. I do have some meetings on Zoom. I'm about zoomed out. But, you know, we did get some good information today on the ratio test. We did prove some good things, and you did get a good dose of it. But like I said, I think the idea is to see a little bit more algebra from the different situations and get comfortable with dealing with some of these factorials. And they're not too bad. If you know the definition, you're gonna use, what you're gonna see is a lot of things are gonna cancel out. And Kirby, let's see, where was the last part here? Yeah. Here we go. Kirby, yeah, we also say converges, and this is by the ratio test. We got absolute convergence. Yeah. Let's do this. Here's what we can say, because sometimes they're going to say to you to justify your answer, right? Because people guess. They just say converges, diverges, and then do a little funny algebra, and they think that's the work, you know? And you have to show work for credit, which is why you have to read all these things, and it's a pain. You got to go into the details, because at this point, people just say, converges, and they do algebra that's not even valid. And they just guessed, and they want full credit, right? And it's like, no. So you got to know what you're doing. In other words, do the algebra. This is, you know, you're competent, and you should always work on that competency. But anyway, that's a whole other thing. But yes, we can say we have absolute convergence, right, by the ratio test, which is, again, if you have absolute convergence, you have convergence. So you say, i.e., convergence. Even if you said you have convergence by the ratio test, that's okay too. Because don't just say the conclusion, show your work, show the algebra. Right? You got to show this stuff. This stuff doesn't just happen by itself. This is you showing some skill sets, right? You know, and this is why I tell people, it's kind of amazing to me that, and maybe you guys can talk to your younger brothers and sisters or whoever, anybody who'll listen, that in order to really be successful in some of these courses like calculus, you got to know algebra. If you don't know algebra, you're done. You know, you got to know everything that we did there, really how to divide complex fractions and then properties of exponents. And in some ways, the algebra we're talking about here is really beginning algebra, you know. And that's interesting. You know, to me, that's interesting. But yeah, algebra is all over the place. You got to show the work, do the algebra. And then you have some definitions here that we work with, like factorial, and how they kind of work together when you have something like 2n plus 1 factorial as opposed to n factorial. Anyway, I talk too much. So I'll post some more examples for you guys like I've been doing. I think that they're helpful. I have gotten some complimentary emails, so thank you guys for complimenting me on the extra examples I do for you, and putting them online for you. You know, I thank you for the compliments, but I will continue to do that because I think it's helpful, and it'll be a database of examples for future students as well. So anyway, let's give you some homework. And this homework is for what is it for? It's for actually ratio and root. It's ratio and root. So it's 12:6. I think I've been doing homework in black. 12:6. It's like 2 to 28 all. So the homework is actually for today and even tomorrow, because tomorrow we're going to do the root test. So I'm going to show you the second part of this, which is very similar, which really is the root test. And it's the same sort of kind of process, you know. So we'll show absolute convergence by the root test. And then that's actually the only test that remains for us is the root test. So if you have any questions or issues, come to office hours. And, you know, take care. Start to work on some of these. But this is the homework for today and tomorrow. And I will give you extra examples. Okay? So take care. Stay safe. And I'll see you later maybe. All right? Goodbye.